Hey everyone, welcome back to my channel. Today we are targeting one more interesting coding interview question. We have to check if the given binary tree is balanced or not. Now this is a one-liner question, but there are multiple layers to it. To be able to solve it, one must know what is tree data structure, what is a binary tree, and then what is a balanced binary tree. We'll be talking about each of these in this video, so let's get started. Let's kick it off by understanding what are trees. Well, not this tree, we're talking about the tree data structure. So a tree is a hierarchical data structure opposed to arrays or linked lists, which are linear in nature. Though essentially the tree follows very similar concept to linked lists, that there are nodes that point to different nodes. Just how we have a linked list in which a node points to the next node. The difference being for any node in a tree, there can be multiple children and a tree can have multiple branches. So a tree data structure actually looks like a flipped tree. So if I flip it over, so we can see there's root at the bottom and then different branches are coming off of it. That's how you can relate it to an actual tree. But when we talk in terms of data structure, then the starting point of a tree is the root. And then we can have multiple children and multiple branches coming off from the root. There's one more point about trees that is worth mentioning, that trees are unidirectional in nature. A parent node will point to a child node, but a child will not point back to the parent. Let's look at some terminologies related to the tree data structure. So what we have at the top here is called the root element. So root is A. Okay. Then any node that has children is called a parent node. For example, if I talk about parent in this one, then A is a parent, C is also a parent because C has E and F as its children. Talking about children, if I have to specify the child nodes, then we have B, C, D as children of A, and we also have E and F as children of C. Apart from root, parent, and child nodes, we also have leaf nodes. So if I talk about leaf nodes, then B, D, E, and F will come under the category of leaf nodes because leaf nodes are those nodes that do not have any children. So the tree actually ends there. That's the leaf node. Then we can talk about siblings like B, C, D are siblings of each other because they're at the same level. They are all children of A. So B, C, D are siblings of each other. Similarly, E and F are siblings of each other. Okay. Now, here we can see in the first tree, like E node has 3 children and D node has just one child. A is the root. There are multiple parent nodes. For example, A is a parent, C is a parent, E is a parent, and then there are different leaf nodes also. So you know the definitions now. Now we'll talk about what is a binary tree. A binary tree is a special kind of tree which satisfies the condition that each node of that tree can have at most 2 children. So any node can have either 0, 1 or 2 children. If each node in a tree satisfies this condition, then that tree can be called a binary tree. For example, if we look here, A has just 2 children B and C, B again has 2 children D, E, C has 2 children F, G, F has just one child H, G has just one child I, which has 2 children J, K. So each node has either 0 or 1 or 2 children, not more than that. So this can be called a binary tree. So if we look at one single node in a binary tree, it can be represented like this. Looks familiar, looks similar to linked list. So a tree node can have its own data. Then it will have two pointers, one to point to the left child and another to point to the right child. So this can be the left child, this can be the right child. Now, when we're talking about left child and right child, they might be the leaf nodes or they can be a complete tree. So it can be a subtree that it points to. So that's a binary tree. Now, what is a balanced binary tree? Before we talk about a balanced binary tree, we should understand the concept of height of any node in a tree. So going back to our binary tree, we have multiple nodes here and say, I want to know the height of this element or the height of G. So how can we calculate the height of any node in a tree? Now, height is a measure of how many levels are there after that node. So if any node has a height of 1, we know there's just one level after that node. If it has a height of 100, then we know, the tree is very big. There are a lot of levels after that node. So let's try to calculate the height of this G node here. So G has I as a child, which has J and K as children. To know the height of G, we'll start from the leaf node. So J and K are the leaf nodes here. How we know they're leaf nodes? Because they don't point to any other node. They're pointing to null. Now let me denote that by cross here. They're not pointing to anything. To know the height of any node, you need to know the height of its child. That's the most efficient way of calculating the height. So the formula for height is very simple. You just take the max of height of left subtree and the right subtree. So whatever is the maximum of either the height of left subtree or the right subtree, you add 1 to it. That's how you'll get the height of current node. So for K, the height is going to be max of, since there's no left subtree or right subtree for K, it will be max of 0, 0 plus 1, which is going to give us 1. So K has a height of 1. So I can just write it here. Similarly, J, same rule, has a height of 1. Now when we talk about I has two children, J and K, that have a height 1, 1. So for I, the height is going to be max of 1, 1 plus 1. So that's going to give me a height of 2. Now for G, the height is going to be max of 0 because its left subtree is not pointing to anything, and 2 plus 1. So we get height as 3. So the height of G node is 3. Let's talk about C node. To know the height of C node, I should first know the height of its children, which is F and G. I know the height of G, which is 3, but I don't know the height of F. So let's calculate that. To calculate the height of F, I'll first calculate the height of H. So H has a height 1. Then F will have max of 0, 1 plus 1. So F will have a height of 2. So C will have a max of either 2 or 3 plus 1, which will give us 4. So C has a height of 4. Doing the same thing with B, D and E, height 1, 1. This gives a height 2. Now what is the height of this root element? It's max of 2 and 4 plus 1. and that gives me 5. So now we can say the height of this tree is 5, which is the height of its root element. And that's how you calculate the height of any tree. Now a balanced binary tree is a binary tree for which the height difference of left subtree and right subtree for any of the node is not more than 1. Let's understand that in detail. So for any node in this tree, the height difference of its subtrees should not be more than 1. If the height difference for the subtrees, for the left subtree and right subtree of any node is more than 1, say 2, 3 or 4, then it's not a balanced binary tree. So I'll just write down the height of each node here. We have 1, 1, 1. This is 2. This is again 2. This is 3. This is 1, 1, 2. And this is max of 2, 3 plus 1, 4. So if I look at the differences in height of child node of A, then it's the difference in 2 and 3, and we want the absolute difference. So we get 1. So it satisfies the condition of balanced binary tree. And we don't have to check only for the root node. We'll have to check for other nodes also. For example, we have C, D, E here. C has 2 children, D and E. They both have height 2, 2. So the difference is 0. So again, it satisfies the criteria of a balanced binary tree. So what we're looking at right now is a balanced binary tree. If we go back to the previous example, we can clearly see like for BC, we have written the heights as 2, 4. Now for A, if I have to calculate the difference of its left subtree, of the height of its left subtree and right subtree, then that's going to be difference of 2 and 4, which is 2. And since the difference is more than 1, it is not a balanced binary tree. So again, a balanced binary tree is a binary tree in which for each node, the difference in height of left subtree and right subtree is not more than 1. So it's keeping a balance. Okay, let's look at a few more examples. In these 3 examples, let's try to figure out whether they are balanced or not. Starting with this one, we'll start from the leaf nodes. So let me start from the most exterior one that I can see. So here the height is 1. That means the height for this is going to be 2. Height is 1. Height is 3. And I'll also keep calculating the differences. So the difference here is 1. Here the difference is, let me just denote the difference by D. So here the difference is 1. Difference between 1 and 0. Here the difference is 0, 0 and 0. Here the difference is 0. If for any node the difference becomes more than 1, then we can say the tree is not balanced. Okay, now I need to know the height of this. For that, I should first know the height of its children. So I'll go to my left subtree. I need to know the height of this. I need to know the height of children first. So go here. For this, the height is 1 because there are no children. Same, height is 1. With that, the height of this node becomes 2, and the height difference is 0. Difference is 0. Here the difference is 1 minus 1, 0. Now for the root node, its children have a height of 2 and 3 each. So height will be 4, maximum of 2 and 3 plus 1, and the difference is 1. So yes, this is a balanced binary tree. Yeah, could have known it by the label. Let's try the same method on this one. And now I'll just try to take an approach of how our code will flow through this tree. So we go to the root node. We need to know its height. To know its height, we should first know the height of its children. And we don't know that. Now we can pick any child. To know the height of that child, we need to first know the height of its children. So do I know the height of this? No. Can I calculate the height of this? Yes, because it has no children, so it becomes 1. Similarly here, height is 1. Now I know the height of these two leaf nodes. I get the height of this node as 2. But for the root node, I still don't know the height. And I'll also put the difference here as 0. For the root node, I still don't know the height because I know the height of its left child, but not the height of its right child. So to know the height of the immediate right child of root node, I need to know the height of both of its children, which I don't know yet. So I'll calculate the height of this, which is 1 because there are no nodes after it. For this, I don't know the height. I'll move down. Come lift, height is 1. I don't know the height of the right node, so I'll continue moving down. Here lift is nothing, so height is 0. On the right side, it has no children, so I get height of 1. And that gives me the height of this node as 2. Now I can know the height of its parent node, which is the max of 1, 2 plus 1, which is 3. And let's keep noting the differences also. 0, 1, difference is 1. 2, 1, difference is 1. So now for this node, this particular node, I know the height of left subtree is 1 and right subtree is 3. So the height becomes max of 1, 3 plus 1, which is 4. That's fine. But when we talk about difference, now the difference is the difference between 1 and 3, which is 2. And that violates the condition of a balanced binary tree. So this tree is not balanced. Furthermore, if I go one level up, the height is 5 and the difference is the difference of 2 and 4, which is again 2. So this is unbalanced at 2 levels. Now using the same approach, how we went node by node till we knew the height of both the children and then we calculated the difference between heights, we'll follow this same approach to solve this problem programmatically. We'll be writing a very simple code that's going to tell us whether a given tree is balanced or not. And I'm going to use JavaScript to do it. So I'll just go ahead and create a new folder and a new JS file in it. Let's say balanced binary tree. And I create a balanced binary tree.js file. I can execute it using Node. So let me just try that. So let's try to execute it. Okay, all's good, working as expected. Now to begin with the solution, I'll first need a class in which I can store a node of a tree. So class to store a tree node. And let's call that a tree node itself. And now that class can have any data that we want to store in that node. So we'll just set that. Apart from the data, it will have 2 pointers, one to point to the left child and one to point to the right child. So we can just say this.left and it will initially be null. So I'm just initializing it to null. Okay, now I can create any tree like this with some data. And then if I want to, create its branches, I can simply set tree.right equals to a new node. Or maybe tree.left. So we'll come back to this. Apart from this class, we need a function that's going to help us in knowing whether a tree is balanced or not. And what that function is going to do is it's going to do two things. One is it's going to give us the height of that tree from that node. Like if we are passing the root node, it will give us the height of tree. If you're passing it any child node, it will give us the height of that node. Apart from giving us the height, it will also tell us whether that node is balanced or not. So to know if the complete tree is balanced, we should make sure that each node is balanced. So let's call that function getHeightAndBalance. And it can take a node as an argument, which is of type tree node, but that won't work here because this is not TypeScript. So I'll just let it stay node. Now inside this function, as we discussed in the algorithm, to know the height of any node, I should know the height of its children. And to know the height of any child, I should know the height of the children of that child. So, we're going to do it again and again, and that's where recursion is going to come into picture. So I can just say I need left height, which will actually be the height of node's left side. Similarly, right height is going to be the height of node's right side. Now, as I'll keep passing the left and right side, there will come a point when left or right may be null, when we'll reach the leaf nodes. So for that, we'll just put a small check here. If the node is null, then we return the height as 0, just how we did it in the algorithm. Okay. Now, when we have the left height and right height, we can check the difference. The difference of heights should not be more than 1. So let's check that. If math.absolute difference between left height and right height, if it's greater than 1, then we return -1. -1 will signify that it's an unbalanced tree. So if this function returns any other value greater than equals to 0, then that is the height from that node. If it's returning a -1, that is implying an unbalance. So if the height difference is more than 1, return -1, stating that this is an unbalanced node. Otherwise, you have to return the new height. Return the height. And as we discussed, the height is the max of the left node height and the right node height plus 1. So if it's the leaf node, it will be max of 0, 0 and 1. So that will give the height of 1. Now, as we are getting the left height and right height, if any of my child node is unbalanced, then the complete tree is unbalanced. So for that, what I can do is I can put a check here if left height is -1 or if right height is -1. That means if any of my child node, be it the left child node or the right child node, is unbalanced, then my tree is unbalanced, so I'll return a -1. So now this is that function which is going to help us in knowing whether a given tree is balanced or not. So let's create a tree. Let's create a very simple tree. So it has, say, 100 at the root. Then at left we have 50. And then at its right we have 80. Now I'll just try to call the function getHeightAndBalance for the tree. Okay, it doesn't give me anything because I haven't logged anything to the console. So let me first try logging the return value itself. Hmm, return console.log. Oh, it's referring to a different file. Okay, now it gives me the output. So the height currently is 2 and it did not give us a -1. So that means it is a balanced tree. And it is of course a balanced tree because it's just one node at the top, then one at left, right. So let's put a simple condition here. If the height and balance of my tree is greater than -1, then I'm going to log balanced tree and I'll also log the height. Let tree height equals to the return of that function. Else you simply log unbalanced tree, or yeah, unbalanced tree is fine. Okay, let's run it. Balanced tree height true. Okay, the condition will come here. Let's run it again. So it's a balanced tree with height 2. Okay, let's add a few more nodes to it. So I can add to the right side, let's add one more node to its left, which has a value 60. And then we can add one more to the right of right, which has value 90. So it's still balanced with a height of 3. Now, what can I do to make it unbalanced? Okay. So this is how this tree looks right now. Let's try to make it unbalanced. So I'll add one more node to the right of the present right child. Let's say 95. It's still a balanced tree because we've added only one child so far. So we'll add one more now. Maybe to its left side, or let's continue adding to the right side. Okay. Let's check. Getting the height. So if tree height is greater than -1. Oh, it's the absolute function. So we need the absolute, but absolute takes only one parameter. So we'll change it to a minus. So we need the absolute of this difference. That's what we were missing. And it should have gone unbalanced here itself. Try it one more time. Okay, it's balanced. Now we add one more node to the right side. And this is how the tree is looking now. And now it's unbalanced. Now, how can we make this balanced? So currently my right side is heavier than the left side. So if I take my first left child and add anything to it, now it's a balanced tree with a height of 4. So with that, with a small recursive function that gives us the height, and if the height difference is more than 1, it returns -1, we can easily check if a given binary tree is balanced or not. Well, that was easier than expected, wasn't it? I hope this helped you in crossing one more problem from your DSA checklist. Make sure you leave a like and subscribe to the channel for more learning videos. If you have any suggestions, feel free to put them in the comment section below, and I'll see you in the next one.